sorry, hearing some background noise. On a large data set, the output would have resulted in an unmanageable amount of errors and false positive detections. So there's time and efficiency trade-offs in the decision whether to use automated detection or manual methods of analysis. And I think this is the reason that many acoustic studies continue to use manual methods of analysing the audio. A common approach is to use sampling, so setting recorders to sample on a limited regular times, or sampling from continuous audio, but this still results in loss of information. So this is where I think that false colour spectrograms are a powerful tool to scale bioacoustic studies to greater time and spatial scales, and to the study of communities. And in a way bridging bioacoustics and ecoacoustics in studies where automated methods might not be feasible. So the method of visualising audio with false colour spectrograms that I'm showing you was developed by Michael Towsey at the Queensland University of Technology Ecoacoustics Research Group in Brisbane here in Australia. Michael's presented and written about this method over the past few years, and he presented at the last Ecoacoustics Congress in Brisbane as well. So the idea and the methods might be familiar to many here, but I'll give a brief overview of the concepts for those who may not have come across it before. So Towsey developed the concept of visualising long recordings using acoustic indices, so to achieve what is in a sense a form of compressed spectrogram or a summarised spectrogram. And the idea was to use 3 acoustic indices calculated at coarser timescales than in a normal spectrogram to compose a summary long spectrogram. And the acoustic indices that were used and found to be the best combination were the acoustic complexity index, temporal entropy, and the event count. And these 3 indices are mapped to the red, green, and blue colour channels. And it was found this was the best combination because it highlights different aspects of the sound content. So this is the result of this method of forming spectrograms with acoustic indices results in this colourful spectrogram that highlights the dominant sound features in a long recording. This is an example of a false colour spectrogram from one of my recordings, a 12-hour recording. So as in a standard spectrogram, time is represented on the horizontal axis and frequency on the vertical axis. The frequency scale is the same as in a standard spectrogram. So in this case, what you're looking at is on the spectrogram, 1 pixel represents 1 minute of time and about 43 hertz in frequency range. And so it was found that these false colour spectrograms reveal a very useful amount of information and detail about the acoustic content of what's in the recordings. So the colours, patterns that you see at a point in time and a particular frequency range can be related to sound events in the audio. So in this example, what you're seeing here in this nighttime recording, some patterns that I've identified for you. The pink marks down the bottom are made by cane toad calls. The insect tracks in the higher frequency range of insects in this environment are always here. And it's a fairly quiet night, and the blue marks are showing passing cars and the occasional bushstone curlew calling in the green marks, which is a nocturnal bird. And then later in the recording at dawn, you can see the marks of the dawn bird chorus starting up. And so frog choruses in particular is what I'm looking at, and they're well highlighted on these false colour spectrograms. So when I started looking at the set of false colour spectrograms for my recordings and becoming familiar with the patterns, I realised I could start to identify some of the species of frogs that were in the recordings just visually, just by looking at the spectrograms. And this is a better example of some frog chorus activity on another night, showing three species of frogs chorusing, cane toads again most of the night, Latoria rothi, which is the northern laughing tree frog, and Latoria fallax, the eastern sedge frog. So cane toads are particularly distinctive in my data. And in one of my earlier studies in my PhD, I used the false colour spectrograms to collect data on the nightly calling of cane toads just by looking at the false colour spectrograms and scanning through the whole set. And at the risk of offending the entomologists here, I've tagged this recording a quiet night in the sense that there's no frog activity. It's just to show you the contrast between a night when there's no frogs calling to show how dominant the frogs are when they're chorusing. But the insects are there, of course, as always. And through the night, there's just a few duck squabbles, I think, and the dawn bird chorus starting again. So I think to mention the main advantage in using this, this method is that the acoustic content of the recording is revealed in a complete picture. So this provides a tool to be able to quickly scan the images and find those regions in the audio that are of most interest and where you can concentrate your analysis. There is a learning process to begin with to relate the patterns you're seeing to the sound sources, but our brains are very good at finding visual patterns. So, and while I found I could identify many species individually, there are a few species of frogs that appear similar, so need to be manually confirmed. And there's high variability in environmental recordings, so there'll always be uncertainty and unfamiliar patterns that need to be checked. So what I wanted to show you is the practical method that I used, how I went about using the false colour spectrograms to navigate my audio and how I learnt the patterns and analysed my audio. So initially when I started out, I would simply open a false colour spectrogram, and so I wonder what might be causing the pink marks down the bottom in the lower frequency range there. And then I would open the raw audio file in Windows, and I use Audacity, so I would wait a minute, sometimes maybe two, for Audacity to open my recordings because they're quite long recordings, and then open the recording in Audacity and navigate and zoom into the point in time that I wanted to look at. But since my aim was to analyse a lot of nights, I needed to make this process a bit more efficient. So I wrote an R script that I used for quickly selecting segments in recordings and opening short segments of recordings. So I used RStudio, and I designed a routine so that single lines of code could just be run quickly one at a time to open short segments of audio. I didn't want to go into details of the R code here. I'm making it available on GitHub for anyone who's interested. But briefly how it works is, where's my water gone? So a false colour image is selected. Some information is extracted from the file name and finds the matching sound file. I then use an R package called the imager package, which allows interactive selection of pixels on an image. And then I use the QUT analysis program's audio cutter to go and find that segment that I've selected and open it in Audacity. So it's a lot quicker process to selecting and immediately finding and opening. So I've done a short demonstration video just to show you in real time what this looks like. Hopefully it works for me. Yeah, so first I run a line of code that opens the false colour spectrogram I want to work on. And then that will find the matching sound file. And then I run the imager package function that will open the image. And I can use the crosshairs to zoom in and select the minute that I want. This will return the X and Y coordinates on the image, but I'm only interested in the X time coordinate. And it then opens the file in Audacity. And I can check that pink mark that I wanted to check was actually cane toads calling by playing the sound file in Audacity.
2 minutes remaining, sorry.
2 minutes, is it? Okay. Thanks. So it's quite a simple script that I wrote just for my purposes, but I think there's others who might find it useful, and it demonstrates that the process can be made efficient. And I could see it being improved using a nice shiny R app. So I just wanted to quickly describe how I've used this to collect the data on the chorusing of the frogs in my, my audio. So I've collected data on nightly chorusing, times and duration. I've detected 17 species, analysed 3 nights over the study period of 2 wet seasons. So I've analysed over 1,300 long recordings. And this is preliminary results, but I've been able to describe the chorusing patterns of different species over the study period and get an idea of their breeding phenology. And I'm using it also to investigate environmental factors that will influence the chorusing behaviour. So just to wrap up, I think this method has some general applications that, that researchers might find useful. It will be useful for simply scanning recordings for events of interest, but also eliminating those recordings that, that aren't of interest or where audio may have failed. It facilitates targeted sampling. So rather than random sampling or blind sampling, you can target regions in the audio where to concentrate your effort and reducing manual analysis. And by doing this, it also allows scaling the studies to communities and longer time scales. And it is also making use of continuous recordings and studying species in the context of the soundscape and what is happening in the whole soundscape. And I have found species identification is possible, especially for chorusing species, because their calls are persistent over time and leave consistent visible traces in the false colour spectrograms. And just a few also considerations to point out. There are some computing resources and time required to initially generate the false colour spectrogram. So the QUT Ecoacoustics lab generated the false colour spectrograms for me. And I think on my data set, I think it was about a 2-week processing time. But once you've got, that's including acoustic indices that you get as well. So once you've got that, that's a permanent data set you can reuse. The patterns do need to be learned, but my R script greatly increased my efficiency once I worked out to do that. I could work through it so much faster. It is a tool to aid manual analysis, so it's not an automation tool, but the software tools are open source. Everything I've used, the QUT analysis programs, is open source, as well as R and Audacity. So that's pretty much it. Thank you very much for listening.
Wonderful. Thank you, Sharon, for a nice talk. We have a few questions. Roseanne asks, have you noticed differences in indices for different type of events, for different type of frogs? Should we use different indices?
So, sorry, should we use indices for if we have different target species? Is that what the question is?
Yeah, the question was about, first, nice talk, thanks. And then,
I think I found it now.
You found it.
I missed the start of it, sorry.
I mean, Roseanne asked what indices were used. I think you said a few of them. And then have you noticed differences in indices for different types of events, frog, insects, and so on? Okay,
so the 3 indices that are generally used in the QUT programs is the acoustic complexity index, and temporal entropy, and the event count. And Michael Towsey did do a fair bit of work to work out that they were the best combination for generally highlighting biotic features, biotic sounds in sound recordings. Have I noticed the differences in indices? Carlina Indraswari she was a research student at QUT, and she wrote a paper, I think, related to this, where she did look at which indices differentiated a few 3 frog species. Or I suppose I can say from my observations, yes, different indices. Different indices are. The colours are quite consistent. So the colours that are in the false colour spectrograms are reflecting what indices are highlighting those features. And a lot of the sounds the frog species are very consistent. So cane toads have a bright pink, which means that they're when they're calling, they're quite high on the acoustic complexity index, which is mapped to red. So yes, I have noticed that there are certain different features as far as call rate, call structure that will reflect the colours differently, but it's quite consistent. Does that answer the question?
I think so, yeah, thank you. In the Q&A feature, Thomas said, wonderful work. Could you talk about how long does it take to generate the fall color spectrogram? Is something that requires heavy computing?
It can be done on a home PC. I've generated them. And I think just on my PC at home, off the top of my head, a 12-hour recording takes about 7 minutes. So it calculates a whole suite of acoustic indices and generates the false color spectrograms. So obviously, the more data you have, the bigger your sound files, the longer it's going to take. But it can be done on a PC. It's just on very large data sets. I think I would recommend some kind of more powerful computing resources. It really
so for those interested in using this useful tool, are you planning to publish a guideline to make available this code?
Yes, so I'll put up that last screen again.
Mm-hmm. If you emphasize that, I think.
Share that again. Where is it? There we go. Can you see that there? Slideshow, right side. So I put up the QUT has a page on GitHub where their analysis programs are available as well. Oh, and I've missed I've made a typo there. Anyway, so yeah, audio analysis programs on GitHub. And I recently put I've got 2 R files that I put up as well, my script and the functions that sit behind it are up there as well, just for people to use if they're curious to even just know what methods I used. And I'll be putting a new version up as well too.
Wonderful, wonderful. Thank you so much, Severin, for the talk.